Alex Cohen. He's a grad student at MIT, and he's going to speak about an optimal inverse theorem for tensors over large fields. So please go ahead, Alex.
Okay, great. Yeah, thanks for having me here, and I'm sorry I couldn't make it in person. That would have been more fun. Yeah, okay, so I'm going to talk about an inverse theorem for tensors over large fields. So the first part of this talk is going to be a bit of...
Yeah.
What was that?
We're just increasing the volume.
Oh, okay. Yeah, so the first part of this talk is going to be a bit of background because I didn't know how much to include in the talk from before, so some of it is probably going to be a good bit of review for this audience, but hopefully that's okay. Okay, so just to introduce kind of the basic notions and what we're going to say about them. So a tensor is a multilinear form that takes in k vectors and outputs a scalar. It's probably something we're all familiar with here. And there's several different types of rank that one can associate to a tensor. And so one of those is the analytic rank, which somehow measures some bias or randomness. And another is the partition rank, which measures some kind of algebraic structure in the tensor. And so our main result is kind of an optimal relationship between these two quantities over very large fields. So it's not too hard to show that if the partition rank is small, then the analytic rank is small, which is kind of saying that structure implies bias. So the interesting part is to prove an inverse theorem saying that if the analytic rank is small, then you can actually explain all of that bias through some very particular algebraic structure in the tensor. And by the way, yeah, if there's any questions, interrupt me. I can't like see the audience right now. So if there's like raised hands or something, I won't be able to see it. So maybe if someone could like tell me if it's a raised hand or just interrupt me because I want people to.
Yeah, we'll shout if
Great. Yeah, good. Okay.
So analytic rank is the most partition rank. That's the easy direction. That's an easier, right?
Yeah, that's the easier direction. The analytic rank is the most partition rank. Okay, so the main proof idea is that we're going to work over the algebraic closure and use kind of, algebrogeometric ideas, tangent spaces, derivatives, things like that to construct our partition rank decompositions. And so this is where the large field size comes in, is that, right, heuristically, the larger the field, the closer it is to the algebraic closure. And so that's kind of why we need to use large fields, is because we're approximating this, we're trying to approximate the algebraic closure of the field. Okay, so to start off, we're going to talk about the bias of polynomials, which is the notion that leads to the analytic rank of tensors. Let's get my photos at the time. So if you have any, and this holds for any function, not just a polynomial. If you have any function that takes its values on a finite field vector space in a finite field, its bias is just the expected value of a character applied to f. So I think I have a picture here. Right, okay, so the character applied to f is going to be some value on the unit circle. So for instance, if this is a prime field, then it just kind of maps 0 to 1, and then it maps it all around the unit circle. And so the bias kind of measures how biased the output distribution of the character chi of f of x is. And in particular, if f is a polynomial, then one can show that the bias is a real number, and it's between 0 and 1. So the bias being large is the same as the bias being close to 1. And you should think about bias being small as some lack of any randomness, as a presence of randomness or lack of correlation, and bias being large is some unexpected correlation between the outputs. So kind of the goal here in this little area is to explain any large bias in a polynomial function by the presence of structure. And this fits into some larger theme of explaining large bias in any function by the presence of structure. But for this talk, we're just thinking about the special case where f itself is a polynomial function with some fixed degree.
Alex?
Yes?
Why is it real for polynomial?
So okay, I have to think. I maybe should have said for a tensor.
For tensor, yeah.
Wrong, but it's real for a polynomial in general. It might be for a tensor.
Okay, thanks.
I'm sorry about that.
Maybe for polynomial it's not, but for a multilinear polynomial.
Yeah, multilinear polynomials are the ones we're going to be working with. And in general, you can kind of reduce to that case.
Right.
It might be real for polynomials in general, but I don't know off the top of my head. But we'll see why it's real for tensors, at least in a moment. Yeah, good question. Okay. So I'm going to talk about analytic rank. So, right, so we're focusing on a very special class of polynomials, which are, well, not very special. It's kind of special, but not very special class of polynomials, which are the multilinear ones. So it's polynomials that take in k vectors, x1 through xk, and the output is a multilinear function of those inputs. So, in particular, one tensor is just a linear function. So it's specified by some list of coefficients for each of the coordinates of that just single input vector x. A true tensor is a bilinear form. So it's a degree 2 polynomial, and it's specified by some matrix, right, which kind of specifies the coefficients of, xi times yj. And a 3 tensor is a trilinear form, so it takes in 3 vectors and outputs a scalar, and it's specified by some kind of 3D grid of coefficients. And so in general, a k tensor will be specified by like a k-dimensional matrix. And it's a useful class of degree k polynomials. So the analytic rank is defined in terms of the bias, and it's defined to be the negative log of the bias. So the smaller the bias, the larger the analytic rank. And the larger the bias, the smaller the analytic rank. So analytic rank small means that there's some unexpected bias in the tensor. Okay, so a few basic properties. The first is that it lives between 0 and n. So, at first you might be worried, what if the bias is super close to 0, then it could shoot off to infinity. It turns out that if there's only n variables, so here n, right, if you have a linear form and x lives in f q to the n, then n is like the number of variables, not the number of input vectors. Does that make sense? Right, it's like the dimensions of matrix, not the number of, it's like the size of the matrix, not the number of dimensions in it.
Right.
So analytic rank lives between 0 and n, just like the normal rank of a matrix. It's sublinear. And by the way, this sublinearity is kind of what leads to the analytic rank being bounded by a function of being less than equal to the partition rank, which we'll get to later. And for a generic tensor, the analytic rank is around n, which is its maximum value. I'm just going to sit here for a second so people can digest these definitions. So here's a nice example. A nice type of tensor is a 2 tensor, which is the same thing as a matrix. And it turns out that in this case, the analytic rank agrees with just the normal rank of a matrix, which is a good thing. Right? In general, there's so many ways to define the rank of a matrix, and they all agree with each other. And lots of those ways will lead to different notions of rank for a tensor. But all our notions of rank should give the standard rank of a matrix. So, okay, so here's why. So we want to compute this expected value of the outputs. And we're going to do that by first kind of inputting some vector x and then inputting some vector y. And the idea is that if x transpose times a is the 0 vector, then chi of x transpose times a times y is always 1. But if x transpose times a is not the 0 vector, then x transpose times a times y is uniformly distributed in y. So that expected value over x is just 1 if, sorry, I guess I got those a little backwards. It's just 1 if a times y equals 0. And otherwise, it's 0, right? Because, any non-zero coordinate in y will lead to x transpose times a times y being uniform over the unit circle as x varies. So the bias is just equal on the nose to the probability over all vectors y that a times y equals 0. And this is some kind of analytic version of the codimension of it's some measure of the size of the kernel of A, and the kernel of A is related to the rank. And so, right, you can just compute this as its size of F to the negative rank of A. And after taking the negative log of the bias, we get of the tensor T is equal to the rank of the matrix A. Okay, does that calculation make sense? I wish I could see people's faces right now.
People do not. People are nodding.
Good. Okay. Good. Okay. So here's another example. This is a singleton tensor. So this is now a 3 tensor. And right, so if you think about it as a 3D matrix, it's going to have one non-zero entry. And we're going to do a similar thing. If we first put in the vectors x and y and then put in the vector z, then we see that that expected value over z is going to be 0 unless x1 times y1 equals 0, in which case the expected value over z is 1. So it's just a probability that x1 times y1 equals 0. And we can just count the number of times that occurs and see that it occurs with probability like 1 over the size of the field F, leading to an analytic rank of 1, which again is smaller than we would expect in general. It kind of makes sense because it has just one non-zero entry. And okay, final example is the diagonal tensor. So this one, right, if you imagine like if it's a matrix, then it just has ones along the diagonal. If it's a 3 tensor, then it has ones also along that that diagonal. And we do once again a similar calculation, but this time the bias is the probability that x1 times y1 and x2 times y2 all the way through xn times yn equals 0. And in this case, it's kind of n independent copies of the probability we computed for the singleton tensor. And so it's like the probability goes like 1 over size of f to the n. And so the analytic rank is around n, which is the maximum possible value, which again is what we should expect. So, make sure I'm okay on time. Okay, so these calculations lead us to a nice way of a nice interpretation of the analytic rank of a tensor in terms of its kernel. So the kernel, I'm just going to find the kernel for a 3 tensor first, and then the definition for a k tensor is kind of clear. What we do is we view our tensor not as a function of 3 input vectors, but as a function of 2 input vectors that then kind of its output is a linear form in Z. So the kernel is the input vectors x and y, whose output is a 0 linear form. And so this is the same thing as kind of the common 0 locus of n bilinear equations in x and y. In general, for a k tensor, it's the locus of k minus 1 input vectors, whose output in T is the 0 linear form. Right, so this is kind of some, just like the kernel of a matrix is some linear variety, the kernel of a tensor is going to be some nonlinear variety. Okay, and there's an exact formula for the analytic rank in terms of the size of the kernel, which generalizes the calculations from the prior slide. So here's, I have like a 1-line little formula showing this, but it's, right, the equation is it's k minus 1 times n, which is the total number of input variables, because there's n variables for each xj, and there's k xj's, k minus 1 xj's, minus the log of the size of the kernel. And the idea here is that this should be viewed as some kind of analytic version of the codimension. Because if the kernel were a linear variety, then the number of elements would be size of f to the dimension of the kernel. And so taking the log is like an analytic version of the dimension of the kernel. And so then subtracting that from k minus 1 times n is like an analytic version of the codimension of the kernel. But anyways, the point is that the kernel is large if and only if the analytic rank is small, right? Which is analogous to the case of matrices. The kernel of a matrix is large if the rank is small. Okay, just going to give a chance to any questions so far. Okay, now I'm going to move on to the partition rank, which is another notion of rank. Okay, recall that a matrix has rank 1 if it's an outer product of 2 vectors. And this defines what a rank 1 matrix is. And in general, a matrix has rank R if we can write it as the sum of R rank 1 pieces, as some of R outer products. And so the rank is the minimal such R. Generalizing to tensors, we can take the outer product of 2 tensors in an analogous way. We say that partition rank 1 tensors are the tensors that are an outer product of 2 smaller tensors. So this is kind of a little toy example for the case of 3 tensors. And so partition rank is the minimal R, so that T is the sum of R partition rank 1 tensors. Now, there's a distinction between the notion of partition rank and slice rank, which I want to mention on the next slide. But for 3 tensors, they're the same thing. Right, okay, so I'm just going to put the next formula. So a tensor is partition rank 1 if the product of 2 tensors in disjoint subsets of the variables. So the case of slice rank is when we only allow 2 subsets of the variables where one of them is a singleton and the rest is everything else. But for instance, for a 4 tensor, we could have a partition rank 1 piece, which is something like f of x1 comma x2 times g of x3 times x4 to x3 comma x4. And that tensor could have full slice rank, but partition rank just 1. But in general, it's these pieces, right? This fj is a tensor in some smaller number of variables, and this gj is a tensor in some smaller number of variables. And so this is what a small partition rank decomposition of a tensor T looks like. Right? These are our structured components, or these pieces here. Oh, okay, right. So I have this example that I just said in the prior slide. This is an example of a tensor with partition rank 1, but has full slice rank. It's like a product of 2 diagonal tensors and 2 variables. So some basic properties. The partition rank also lives in the range 0 to n, just like the analytic rank. The analytic rank is less than the partition rank. And here I have some kind of toy calculation along these lines. So, for example, if T is a 3 tensor and it can be written as a product of a linear form and a bilinear form, then in order to find input vectors x and y that lead to the output 0, it suffices to just have f of x equals 0. And so what initially was going to be the vanishing locus of n different bilinear equations in x and y, it turns out that the vanishing locus of just one linear equation in x is enough to find pairs x and y in the kernel. So the codimension is kind of like the number of equations you need to cut out the kernel, and it turns out we can cut out a subset of the kernel with just one equation. Okay, and similarly, if we have a 3 tensor with partition rank 3, rather than needing n equations to cut out a subset of the kernel, as long as f1 of x equals 0, f2 of y equals 0, and f3 of x and y equals 0, the pair x and y must lie in the kernel, So in general, for any partition rank 1 piece, there's going to be some part that has z in it and some part that doesn't have z in it. And the part that doesn't have z in it is some tensor in x and y. And if we set all of those pieces equal to 0, then each partition rank 1 piece has to vanish. And so if it's partition rank r, then we have r equations that cut out a subset of the kernel, leading to codimension r. So, okay, so that's kind of a heuristic idea. In order to make this rigorous, one needs to show that if you have just r multilinear equations in x and y, that you really can find a lot of genuine vector solutions to those over the field FQ. And those plentiful solutions lead to small analytic rank. And so that's kind of how the proof goes, by finding lots of solutions to this system of equations over the finite field FQ. And again, then when k equals 3, the partition rank agrees with the slice rank because there's always some linear form factor. Okay, so does that make sense so far? Those are kind of the basic notions. So I want that to all make sense so far. I can't see anyone's faces, unfortunately. So I'm gonna assume it makes sense.
I think people
Okay. Okay, so now I'm going to talk about the main theorem. So prior work has asked questions like, can we bound the partition rank in terms of just some function of the analytic rank? So given that T is biased, can we conclude that it has some structure? This is the simplest case of the inverse conjectures for the Gowers norms in additive combinatorics, where in general, the inverse conjecture for the Gowers norm asks about bias versus structure for arbitrary functions T, and one needs some more sophisticated notion of structure here rather than this very simple algebraic one. And this is kind of the simplest case when the input functions are themselves polynomials. So, okay, so the first result of this form was obtained by Green and Tao, and then further improvements over the fields was obtained by Kaufman and Levitt and Levin and Boehmwick. And they proved that the partition rank is indeed bounded by some function of the analytic rank, but that function is of Ackermann type. So this is really a qualitative sort of theorem rather than a quantitative one. Harmati and Spielka showed for 3 tensors, the partition rank is bounded by constant times the analytic rank to the 4th power, so some polynomial bound. And then there was a breakthrough by Milicevic and Janzer, who proved that the partition rank, independently proved that the partition rank is bounded by the analytic rank to some power. So the partition rank is bounded by a polynomial function of the analytic rank. And it's been conjectured by several authors that partition rank is bounded by a linear function of analytic rank. And if this is true, this would kind of be an optimal relationship and would explain, qualitatively, it would explain all of the bias in terms of partition rank. So the main theorem we prove is that this conjecture is true over large enough fields, where again, we have to work over large enough fields in order to make the analogy in order to work over the algebraic closure in a suitable way. So partition rank is bounded by some constant times analytic rank, and then there's a Sully plus one. And the size of the field depends on two things. It depends on the order of the tensor, and it also depends on the analytic rank. So what this says is that assuming the analytic rank is small, if the field size is large enough in terms of the analytic rank, then a partition rank is small. So 3 tensors came first. And in this case, it works over all fields due to a result of Dirksen, who I think is here, which kind of makes the field definition question irrelevant. And this was independently done by Adeposito, Kashtan, and Ziegler as well for 3 tensors. We go through a smooth analog of the analytic rank called the geometric rank, which I'm going to talk about in the next section. And there's also been some very exciting, very recent work by Moshkovitz and Zhu, which removes the large field size assumption at the cost of a polylogarithmic factor. And yeah, I haven't really read that paper yet, but it looks very cool. Kind of the general sketch of the argument is, right, we have these 3 quantities: partition rank, analytic rank, and geometric rank. And by the way, this picture is kind of a cartoon. This isn't exactly how it goes, and we'll refine it later. But the general idea is we start with a tensor. We know it has small analytic rank. And then we prove that this geometric rank is small as well, which kind of says that the smooth picture is a good approximation for the finite field picture. And then that's where we kind of use the large field assumption. And then we prove that if the geometric rank is small, we use that to locate a good partition rank decomposition. And this is kind of the heart of the proof. And here we look locally near a point and apply these algebrogeometric techniques. So now for the geometric rank. Okay, I said the word codimension a few times already, both in talking about the analytic rank and the partition rank. And the geometric rank is just defined to be the codimension of the kernel of the tensor T, which kind of naturally generalizes the definition of the rank of a matrix as the codimension of its kernel. So for the case of a 2 tensor, it's just the same as the normal rank. It's the we have the definition after this. So recall that we have the kernel of an arbitrary tensor. It's some nonlinear variety in general. And we can just ask what is the codimension of that variety over the algebraic closure, and that's the geometric rank. So this is a notion that really makes sense over the an algebraically closed field, because those are the sorts of fields in which the notion of codimension in algebraic geometry is well behaved. So a few comments. So we could, here I've been writing the kernel of the tensor T, but there's really several different kernels we could take, because we could take the first k-1 vectors to be the input and kind of the last vector to correspond to the output, but we could slice it differently and take the last k-1 vectors as the input and the first one as the output. And so we could have a whole k different possible kernels of the tensor T, but it turns out that all of these kernels will have the same codimension, even though they'll be different varieties. So the geometric rank doesn't depend on how we slice the tensor T. It really only makes sense over algebraically closed fields. And it's not too hard to show that the geometric rank is less than or equal to the partition rank. And the reason is for the same reason that I explained before, that the analytic rank is less than or equal to the partition rank. If the partition rank is R, then we can find R many equations, the common vanishing locus of which lies in the kernel. And if you have R, the codimension is a measure of how many equations you need to cut out the kernel. So if you can find these R special equations, which happen for partition rank to be multilinear, that cut out a subset of the kernel, then the kernel has codimension at most R. And recall the codimension is just the dimension of the ambient space minus the dimension of the variety. So here I just have a little cartoon. On the left is a nice linear variety, which is like the kernel of a vector, sorry, a kernel of a matrix. And on the right, I have some curved variety, which is like the kernel of maybe a 3 tensor. And this isn't really what it looks like. It's just a cartoon. So you don't have a flat, you don't have a flat hypersurface in your mind. So to take an example, let T be the determinate tensor. So this is, everyone's favorite tensor. It takes in 3 vectors. It outputs the determinant of the matrix. It has those tensors, those vectors as its rows. It's, alternating, multilinear, etc. And the bilinear map associated to it, right? So the one that takes in just 2 vectors, x and y, and outputs the linear form in Z, is given by the cross product between x and y. This is how the cross product is defined. So, all right, now I have the matrix associated to this determinant tensor. So the kernel is the set of input vectors x and y, whose cross product is 0, which is the set of pairs x and y, one of which is a scalar multiple of the other. And this is a 4-dimensional space because you have 3 parameters to choose x, and then 1 more parameter to choose the scalar multiple of x, which is y. And so the geometric rank is 6 minus 4 equals 2. So it does not have full geometric rank. But on the other hand, one can show that this tensor has full partition rank of 3. So this is a case in which the geometric rank and the partition rank are not the same, right? In general, they're not equal. Okay, we're going to get this in a moment, but what we're going to show is that there's a very nice, kind of the nicest version of the proof that we're talking about is a proof that the partition rank is bounded by a constant times the geometric rank. And the whole business of talking about analytic rank versus partition rank kind of goes through this proof method, which, the proof method kind of inherently works over the algebraic closure, and thinking about analytic rank is a matter of showing the algebraic closure is a good approximation to the field itself. Okay, does the geometric rank make sense?
Mm-hmm.
Okay. Now, once again, feel free. I'm just going to pause for a second. So if people come up with questions, they can ask them. Cool. I hope that means that this has all been going too slow rather than too fast. Okay. So, right. So I'm putting the 2 definitions of analytic rank and geometric rank right next to each other, so that we can, see how they're similar, right? And here we're going to see that thing I said earlier, that the log base f of the size of the kernel is like an analytic version of the dimension. And right, a justification of that, I said before, is that if the kernel is a linear variety, then you can just count the number of elements, and it's just the field size to the dimension, right? Because for instance, if you have, this is just like counting the number of points in fq to the n, it is just q to the n. That's what this is saying, right? And so the point is that log base f is just the dimension. And so in general, we expect this to be true, something like this to be true for arbitrary varieties. And there's a kind of a precise result in this direction, which is the Lang-Bay bound, which we don't use exactly, but we use related ideas. But that just kind of says that the counts of f points really is, goes like the dimension. Okay, so the direction of proving that if the analytic rank is small, geometric rank is small, which remember is like saying if there's many points in the kernel over the finite field f, then okay, we're trying to say that if there's many points in the kernel over the finite field f, then the kernel has small codimension over the algebraic closure f bar. Okay, so contrapositive, we want to say that if the kernel has small codimension over f bar, then it doesn't have too many solutions over the finite field f. And the tool we use to prove that is this generalized Schwartz-Zippel inequality, which is an inequality of exactly this sort, bounding the number of solutions to points on a variety in terms of its dimension. And so this says that the number of f rational points is bounded by an equation with 2 quantities. So one of them is this guy, which is the part we're looking for. So that's the number of, right? This part is small if the dimension is small. And then there's a second part, which is kind of like an error term, and it's d to the codimension of v. And what this really is an upper bound on the degree of the variety v. So this factor measures the complexity of the variety v. And right, there's 2 components to the complexity of the variety v. One of them is a degree of the defining equation. So the higher degree of the defining equations, the higher complexity the variety is, and the less to be expected to behave like a linear variety in terms of solution counts. And the other is the codimension. And somehow the larger the codimension, the higher the complexity as well. And that's, maybe not totally obvious, but it turns out to be a statement that can be made rigorous. Right. So for instance, you should recall that because a finite field is finite, the n-dimensional vector space, the Driscoll topology in the n-dimensional vector space is discrete, and so any set is a variety. But a set, just a generic subset of fq to the n will have very large algebraic complexity in that if you want to define it as a zero, as the zero logos of some polynomials, then you're going to either have to use very high degree polynomials, making D large, or it's going to have to be like zero dimensional, making the codimension large. And in either case, this complexity term blows up. So this inequality is only useful if you can control both the degree and the codimension, which in our case we can, right? We're saying that right, the kernel is cut out by degree k minus 1 equation, so those aren't too bad. And control in the codimension, well, that's control exactly on the geometric rank. So if the geometric rank is small, then we can get some favorable estimate on the number of elements of the kernel over the finite field, which then gives us some lower bound on the analytic rank. So geometric rank large implies analytic rank large. So, sorry, was there a question?
No, it was an email. I think it was, yeah. Maybe it's your computer.
Okay, so, make sure I don't disturb.
Maybe there's a question in the email.
Okay, so, all right, so this is the theorem I alluded to before, which again, this theorem takes place over an algebraically closed field, which is not our main interest in the talk, but is kind of the way it works technically. They go through algebraic closures. We're saying that the partition rank over the algebraic closure is bounded by constant times the geometric rank. So, okay, maybe I should have emphasized this more when I define the partition rank, but partition rank is a quantity which depends on the field's definition. So you could have a tensor whose entries are in the binary field F2, and it might well be that it has a partition rank decomposition over the algebraic closure of F2, which is smaller than any partition rank decomposition over the finite field F2 itself, because you're allowed more partition rank 1 pieces over the algebraic closure. And it's not known if the partition rank, it's not known how much it can change after passing through an algebraic closure. There's an open question. Dirksen's results show that for the slice rank, it can't change too much. So this applies to the partition rank of 3 tensors, but for higher order tensors, it's not known how much partition rank can change as you look at larger and larger field extensions. So, right, this theorem cannot be immediately applied to bound the partition rank. Right, we're interested in partition rank decompositions over the base field itself. So this theorem cannot be immediately applied. Give an idea of the proof. The proof works locally. So we pick a point on the kernel of the tensor. We take tangent spaces, derivatives, etc. I'm going to try and give a sketch of this at the end of the talk. Similar results appeared in work of Schmidt from a long time ago, which was a surprise to me and Guy. We hadn't heard about this until later, which is, kind of cool that he was working on similar things for number theory problems. And right, a key part of our work is adapting this algebraic closure strategy to work over the base field. And here we are going to accept some dependence of the base field on the analytic rank, but we will not accept a dependence on the number of variables n.
Was Schmidt over the complex numbers or over all, like over other fields?
It's unclear. I think, I'm not sure. I think there's some debate about that.
Yeah, right.
Yeah, to be honest, I have not read Schmidt's proof carefully. So I don't know how much work it takes to make it work over. I think he stated it for the complex numbers, and I'm not sure what it takes to make it work over other fields. Right, but okay, so here's the kind of variant of this theorem that's going to let us work over finite fields. So if X is a subset of the kernel, which is defined over a finite field F, okay, right, so that means that X can be cut out by equations, which have coefficients in the finite field F. And X has a non-singular point, and non-singular is some algebrogeometric condition I'm going to talk about. Then the partition rank is bounded by the same constant times the codimension of X. So in other words, if we replace the entire kernel by some subvariety of X, which must be defined over the base field, and it must have a non-singular point over the base field, then the same recipe gives a partition rank decomposition, which this time will be over the base field, right? So in order to build this partition rank decomposition, we need to kind of take derivatives at a non-singular point and stuff like that. And so if the non-singular point we start with is defined over the algebraic closure, the partition rank decomposition will be defined over algebraic closure as well. And but if the non-singular point we start with and the defining equations are over the finite field F, then so will the partition rank decomposition. Okay, so this is the version that we apply to actually say something about analytic rank and partition rank over the base field. Okay, so there's kind of two parts to our argument, and this is right, kind of a version of it that came up with since we wrote and submitted the paper. So this is, I think, a little different and a little cleaner than what we wrote in the paper. So I can try and actually sketch the proof to you here. I'm going to work with polynomials now rather than tensors. So if I have a polynomial that takes in a vector in f to the n and outputs a vector in f to the m, right? So it's a, it's defined by m polynomials, one for each coordinate. We can take, various derivatives. So the derivative of f will be some linear map, and the kth derivative will be some k linear map. And right, the derivative will, for instance, be a matrix whose entries are polynomial functions of the input point. So the kth derivative in general will be tensors, the entries of which are polynomial functions of the input point. But if f has degree k, then the kth derivative is a constant tensor, so it doesn't depend on the input point. So there's two, I'm sorry. Okay, so there's two components of the argument. The first, theorem A, is like the part on the last slide. And this says that if f is such a polynomial, and here, right, here I'm working with derivatives of polynomials, which are tensors. So tensors are shown with derivatives of polynomials, and in the proof itself, the input polynomial f is itself some tensor, and the derivatives are also some tensor. And so, somehow the kth derivative of a k tensor is itself a larger k tensor, which kind of is determined by and contains the k tensor we started with, but it's different. And so anyway, things can be kind of cleaned up a bit by just working with polynomials in general. But we have some polynomial f, and x is a variety on which f vanishes. Okay, this irreducible assumption, I think we need that, but I think we can assume it for the next part. So we have some irreducible variety, and f vanishes not irreducible variety. Remember, f here has m different components, so that means that all these m equations all vanish on x. Then what I'm claiming is that the partition rank of the kth derivative of f, which is some k tensor determined, defined at the point x, and the k tensor varies with x, is less than or equal to 2 to the k minus 1 times the codimension of x for all non-singular points in x. Okay, and so the way this theorem works is inductively. So we start by proving this just for the first derivative, and then using this partition rank decomposition, we kind of differentiate the partition rank decomposition from the last step to get the partition rank decomposition in the next step. And if everything is defined over FQ, meaning f is defined over FQ, x is defined over FQ, the non-singular point is defined over FQ, then so is the partition rank decomposition that we obtain. Okay, so that's theorem A, which is analogous to the theorem I wrote in the last slide. And theorem B is kind of obtaining this variety x to work with. So if we have some variety x defined over a finite field, and it has bounded complexity, meaning bounded degree, essentially, then we can find an irreducible variety, which is defined over the finite, which is contained in x. It's defined over the finite field, it contains a non-singular point, and it has codimension controlled by the number of f rational points in X. Theorem B is really where we need the large fields, and then theorem A is applying that to construct the partition rank decompositions. So I have a little flow chart. Okay, so this is a little flow chart of how this proof strategy works. So we suppose the analytic rank is small. We want a small partition rank decomposition. We initially set X to be the kernel of the tensor T, the full kernel. We know at the beginning that the codimension of X is bounded in terms of the analytic rank for that same Schwartz-Zippel argument I described before, right? X contains all the f rational points. Its complexity is bounded. And so if it had small dimension, the analytic rank would be large. Therefore, if the analytic rank is small, we know X can't have too large of a codimension. Does X have a non-singular f rational point? If it does, then we can use theorem A at this point to construct our partition rank decomposition. If not, this flowchart on the right is theorem B, then we can find some smaller variety contained in X, which contains all the f rational points and which has larger codimension. And we can try again. And so this is like, you may have heard of energy increment or density increment arguments. This is like a codimension increment argument. Right? If we can't use theorem A, then we can kind of find some smaller variety y in X, which has larger codimension, but still has controlled complexity and all that. And so then the idea is that using the large field assumption, this process can only be iterated some bounded number of times, right? It can't be iterated too many times, because if it was iterated a lot of times, then we get a variety with really small dimension, which contained all the f rational points, and also has bounded complexity, which would mean that there wouldn't be too many f rational points to begin with. We know there's a lot of f rational points to begin with. Yeah, and so this is where, right, it's this procedure where we need the very large fields. The reason we need such large fields is that in this procedure, the complexity remains controlled, but it goes up quite a lot. And so in order for this Schwartz-Zippel lemma to be effective, the size of the field needs to be very large compared to the complexity. And so that's where this trade-off comes in. This is kind of, I think at this point I've kind of sketched the main overview of the argument. So I want this all to make sense so far. Please ask me questions if you have any questions at this point.
So Alex, can you get better dependence on the field size if you can control better the number of possible iterations you'd have to go through this flowchart?
Yeah, absolutely. Yeah, this is something I've thought about a lot, and it seems in this recent work of Moshkovitz and Zhu, they kind of get around this issue by doing something more combinatorial. But right, there's some kind of interesting fundamental algebraic geometry over finite field issues you run into. And so, right, this thing I can talk more about if people are interested in it, but it's plausible that in reality, the iteration kind of doesn't go on as long as the worst case scenario, and this could be controlled better and used to get better bounds. But there's some kind of difficult issues at play there. Yeah, that's a good question. Right, I think that this, okay, I don't want to say this too strongly, this is kind of speculative, but I think one should generally expect that if the partition rank doesn't change much under field extensions, then this procedure should be able to be sharpened, and in some way vice versa. I think they're similar questions. That's not precise, that's just kind of the general vibe. Yeah, okay, so I want to talk about theorem A, but what I really want is for people to digest the proof outline that I've talked about so far and those main ideas. Okay, but now I'm going to talk about theorem A, if I pause here for a moment. Oh, was there a question?
No, it's random people outside.
Oh, okay. Maybe they have a question. Okay, so this is a sketch of theorem A. So this is just the same kind of objects that we're starting with. I put them above. I'm just going to prove it. I'm just going to prove it for the case of 3 tensors, but the argument I give here extends perfectly well to all derivatives. So, okay, so here's the base case. So I want to prove that the partition rank of the derivative of f at any point x is less than or equal to r. Okay, so what's going on here? So x is a variety, it has codimension r, right? So, oh shoot, I wish I had the drawing tools of Zoom because I wanted to draw some little curvy varieties here. Darn.
Should be there somewhere. I never use it.
How do I don't have like the Zoom top bar for some reason. That's okay. I'll just try my best. And then maybe if I don't have that much time left. Okay, so we want to build some small partition rank decomposition, right? And this, this should make sense. This is basically like saying, this is essentially the same thing as saying that, and probably I should have said this before, that if a variety has small codimension, then its tangent spaces have small codimension as well. So like the dimension of a variety is the same dimension of its tangent spaces. That's what's going on here. And that's a really fundamental idea in what we're doing. That the dimension of a variety is the same as the dimension of its tangent spaces. So here, the derivative of f is some linear space. The kernel derivative of f is a linear space lying in the tangent space of x. And so, right, the idea is that if x has small codimension, then these kernels also have small codimension. So the derivatives of f have small rank. So, okay, make this precise. We're going to let pi be a projection valued linear map, which depends on the input point x. And for any x in the variety, it projects onto the tangent space. And then 1 minus the projections. This is the complementary projection. This projects onto some complementary subspace. And this is the complementary subspace of the tangent space. So the tangent space is codimension r. So the complementary subspace has dimension r. And so this is a rank r decomposition for the projection onto a complementary subspace. So here these Lj's are linear forms and these Wj's are vectors. And the linear forms and vectors both depend on the parameter x in a polynomial way. And the derivative of f, I'm just writing the vector v in this funny way in terms of the projection pi and these linear forms. But because pi of x is in the tangent space, the derivative of f vanishes vector in the tangent space essentially by the definition of the tangent space, where the tangent space is a set of vectors, the kernel of all the defining vectors of the field. And so that part vanishes, and then we get these r pieces, and these r pieces give a rank r decomposition for the derivative. And so now I'm just writing this vector df of x at w1 of x, blah, blah, blah. That's just some vector. I'm writing that as gj of x. And so then I have some rank r decomposition in terms of a linear form of a vector times a vector. And this r of these pieces. Okay, does that make sense? So that's how we can build some rank r decomposition using kind of the geometry of the variety of x. Our rank r decomposition depends on x. So now we're going to differentiate this decomposition to obtain our decomposition of the 3-tensor second derivative of f. So second derivative of f is a bilinear form. It takes in 2 vectors and outputs a vector. Okay, so we have that for any x in x. Oh shoot, I'm sorry, I have a I missed a condition here. This should say for any v in the tangent space of x at x. That's really important. So this only this equation only holds. Wait, no, I'm sorry. This equation holds for any x in x and for any v. I'm sorry. Back to the next part. Okay, the second derivative at v1 and v2 is, right, if we like put in v1 and think of that as a function of all x, then we differentiate that function in x in the direction v2. Okay, so now the point is that, okay, so this is derivative of f at x in the direction v1 is some function of x. There's an equation for that function that holds for all x in the variety of x. And so if the vector v2 lies in the tangent space of x, we're allowed to kind of differentiate the equation on the variety x. I realize I'm saying the word variety a lot of times without really talking about what that is or drawing pictures, but I hope that's okay just for the last few minutes of the talk. But okay, the real point here, the real calculation is that each of these pieces, when we differentiate in the direction v2, by the product rule, splits into two parts. And those two parts are each partition rank 1 pieces in the 3 tensor. So, right, this holds for all v2 in the tangent space of x at x, and for any x in x. We have this formula for the second derivative. Now, for a general vector v2, we can kind of split it up into two pieces, pi of v2, which lies in the tangent space, and this complementary piece, which doesn't. And this first piece, we have this formula for coming from this calculation above, right? In terms of these R components, using our partition rank decomposition in the prior step, we got these R pieces. And then we have an error piece coming from the part of the vector v2 lying in the complementary subspace. Because the complementary subspace has small dimension, this error piece has small partition rank. And so, okay, this is a little bit of a confusing expression, I grant you. But something that should just kind of appear here as a sanity check is that there's 3 kinds of partition rank 1 pieces for a 3 tensor. And in this decomposition, we have 3 types of partition rank 1 pieces. This one is one flavor, this is the second flavor, and this is the third flavor. And then for higher order tensors, we keep differentiating in the same way. And each time we differentiate, we get twice as many partition rank 1 pieces that come from the prior derivative. And then we get another error piece, which gives us our new flavor of partition rank. And every time we differentiate, we get a new flavor of partition rank coming from this bounded error from the complementary subspace. Okay, so I'm sorry I went a little off the rails there in the last couple minutes, but I hope that made some sense. And yeah, please tell me if there are any questions.
This is the end of the theorem, of the proof, right? So,
Yeah, I'm done.
Let's applaud.
I'm going to go back to a prior slide in case there's questions on it.
Let's see, are there any questions?
Yeah, maybe what kind of bound would you need between the partition rank of the ground field and partition rank of the algebraic closure? Like linear, or is polynomial good enough?
So what kind of bound would you need in order to do what?
Well, you mentioned at some point that if you had a good bound there, then maybe you could get rid of this large field.
Oh, yes. Okay, so you would need to show that the partition rank over some finite field is bounded by a constant times the partition rank over the algebraic. Okay, there's right, that's an interesting question.
So polynomial is not good enough.
I think that is
doable.
Okay, I don't think polynomial is good enough. But let me just think for a second. Right, what I'm thinking about is if I don't think polynomial is good enough. Right, you can get some kind of boost by like applying this to Felix interest from our argument, but I think you need a linear bound, not a polynomial bound.
Is that known for slice rank? Is that what you said? Like for slice rank, are there good bounds for that?
Yes, so for slice rank, Dirksen proved a linear bound for the slice rank over the algebraic closure in terms of the slice rank over the base field.
Okay.
Because the G-stable rank, this table of field extensions, has a constant bound between G-stable rank and slice.
I see. Okay. Yeah, I missed that. I think that part.
But you show a linear relationship, so without bad field size dependence between geometric rank and partition rank over infinite fields. So what do you show for those two quantities?
That's right. So for any algebraically closed field, we have a linear relationship between partition rank and geometric rank, and that is using this theorem A. So exactly this argument I was showing you at the end, right? If you have any variety, you can always find a non-singular point over the algebraic closure due to algebraic geometry. Then you can apply this theorem A and get partition rank decomposition over the algebraic closure, which is bounded by this 2 to the k-1 constant times the geometric rank. You just take x equal to the kernel of T.
Yeah.
So if you look at partition rank at most some number R, then it's kind of a reducible variety where the number of components is polynomial in R. In a similar question, do you think that analytic rank at most R, well, that is also some finite union of irreducible sets that. And do you think this number will also grow polynomially in R?
I'm sorry, I think I'm having a little trouble understanding, I think due to it's like the audio is a little bit garbled over Zoom. Can you repeat the part you're asking about analytic rank? So the number of components of what?
Okay, so every restriction closed property you can write as in a unique way as a union of irreducible restriction closed properties of tensors. And well, in the case of partition rank at most R, that corresponds to the different ways of, partitioning. So that gives you a polynomial number of irreducible components of those varieties. And I'm wondering whether for analytic rank, you also get a polynomial number of irreducible components.
You're saying that, wait, are you saying that the kernel has a polynomial number of irreducible components, or the part cut out by the
I'm saying the variety of tensors of partition rank at most something is some reducible variety, and then the same way you can ask the same question about analytic rank.
So you're saying that the variety of tensors of partition rank at most R has polynomial in R many irreducible components.
Yeah, it's given by parameterizations from irreducible. Okay.
Oh, and you're okay. So, that's an interesting question. So, right, I'm trying to think if there's how to even pose the question due to the analytic rank. Right, the analytic rank is defined over a finite field, but if you take a tensor with entries in some finite fields, but you look at the analytic rank viewed as a tensor over larger and larger fields, that will kind of approach the geometric rank in the limit. So in some limiting case, you're getting just a variety of tensors with geometric rank less than equal to R, which presumably would have the same bound. But I'm not quite sure how to pose the question for analytic rank, but I would guess that for geometric rank, something similar would hold.
Okay, thanks.
Nice. Questions? I think we're happy.
Thanks a lot, Alex.
All right. Thank you for having me.